I'm going to talk about electron box loading, and this concept's kind of interesting. And it start here that we just use numbers and letters, and then we do like even a more augmented version of this. But this is going to explain this whole principle, okay, on how you determine where the electrons are located in an atom. So there's three different principles of electrons. The first one's the Pauli exclusion principle, and for all practical reasons, every orbital we're going to denote with a box. And the box either gets one arrow up or one arrow up and one arrow down. So there's two electrons in each box. It's either arrow up or arrow down. As a rule, you put the arrow up to begin with. And this is kind of an arbitrary thing in the sense that, we're saying it's spinning in one direction, okay? And this has to do with the Pauli exclusion principle. Pauli exclusion principle just basically they can have 0, 1, or 2 electrons in any one orbital, which we show right here, right? And their spins have to be opposite of each other. So they can't have two going up. So I'm going to draw one going up here, and this is wrong. No, international no symbol. Either one up, one down, or just one up. That's all pretty much you get, right? So that's the first rule, okay? So I'm going to talk a little bit about what these orbitals look like, okay? So there's something called s orbitals, p orbitals, and then there's d orbitals and f orbitals. The ones you're going to focus on in this class are s orbitals and p orbitals. S stands for sphere. It's spherical in nature. So looking at this, they have a sphere and shape. And keep in mind, it's not a perfect little circle. It's a cloud. And what it is a cloud saying the electron is like somewhere in this region. It's a probability. It's like 90% of the chance it's going to be somewhere around here within the circle region, okay? And the radius is just going to keep increasing as we go up. Now, to kind of let you know, see this 1s, 2s, 3s, these numbers right here? I'm going to pull up a thing right here for you to see, right? They would be denoted on the sides of this periodic table right here, okay? I'll move this down here so I can see what's going on. This is 1. This is the second quantum number, third quantum number, 4, 5, 6, and the last one's going to be 7. This region here is S. This region from here to here, and I'm sorry my little thing here is in the way, but maybe I can move it over just a smidge. Yeah, that's good. I'm not going to move this thing back, right? This is going to be my P region right here, okay? Over here, this is D, okay? And this last one down at the bottom, this is my F, okay? Generally speaking, S and P make up your valence electrons, and they're the ones, I guess, furthest most, for lack of better words, from the center of the atom, okay? And how we're going to read this is you just read across the periodic table, and we're going to fill these in as we go. There's a diagram I'm going to show you that kind of makes this simple, but you can see what's going to go on, that this would be the arrow up. This one would be arrow down, put that like this. So we're going to actually have this thing as, if we look at the hydrogen by itself, it would have one arrow going up like this. Helium would look like this. And I'm actually not really enjoying the way I put this, and these are the 1s orbital boxes. So we have 2 in here. So this would be 1s2, and this would be 1s1. So, and this is 1s1. That's how we're going to denote it, and you'll see it when I start going through examples how this whole thing works. Okay, so this is the s orbitals. Let's talk about what a p orbital looks like. Okay, they're going to be a little different, but I think before let's talk about what that really means. These have areas that you are not going to really find the electron. They're called nodes, and I don't want to get long-winded about this, other than the fact there's a region where you're going to find them, and all of a sudden there's a little gapped region where you probably are not going to find the electron. Then you find the next group. These are all p's, and the next group would be 3's. So this tells you these are regions where the probability of finding an electron, it's not going to happen. That's in the noded region. Things are not going to exist. It's between the actual spheres, in a sense, right? P orbitals are interesting because they work in several different dimensions, right? They're not just like a sphere is in all dimensions. You can be in the x plane, y plane, or z plane when you're doing P's. Keep in mind these are clouds, but we like to draw them like dumbbells because it looks cool, I guess. I don't know. It's an easier way to understand the shape of these things. So they have two different lobes, right? And the node in between them, it's not going to be located here, and there's no probability of it being here if it's in this orbital. Now, keep in mind, once again, that you could have an electron here and an electron over here. They're going to have opposite spins. Want to go this way, want to go that way, for lack of better whatever. And usually you denote the p orbitals as a box, three boxes together. So you can look at it, it doesn't matter which way they fill. This is X, let's say this is Y, and this is Z, right? So let's make this 2P, right? So it would fill this one first, and we call it, that would be called 2P1. And we want to maximize our upward spin. That's Hund's rule. So the next one would be up. That'd be 2P2. This one, make it 2P3. And then you start loading them down. And you'll see when we go through the examples is that get in a habit of putting all the arrows up before you put the arrows down in any one of these things. You're less likely to make a mistake. So all arrows up before you start putting arrows that go down. Okay. So here's lithium. Okay, very simple diagram. Okay, and if I look at it on my periodical table over here, right, I should move this back over a little bit. In fact, I could probably put this guy right down here in the center. I'm not going to do any of those in the bottom. Okay, lithium, you can think this one arrow up. This is 1s. Oh, put 2 there. I don't want to put 2 there yet. You have 1s here. Okay, and this is the other s over on this side. This is the only one that's a little wonky. Right. So this arrow, that one's going up, this one's going to go down. And so the box diagram for this thing would be 1 up, 1 down. I just showed that to you already. So we call this 1s2. Lithium would have only one arrow going up on the next one. This is the first, this is the second one. So it would have another one like this, one arrow up called 2s1. And we would denote it like lithium. That's why you see in this example right here, it says lithium, one arrow up, one arrow down. And then we have this guy. So if we were to think each arrow kind of being an element, that's when we're looking at this. This would be hydrogen. This arrow down would be helium. This right here would be lithium. We don't do it like this because it gets really messy, but that's what's happening, right? And so that's kind of how this orbital box diagram is going to work. Let's take a look at this. So the Aufbau principle is the building up concept. So number of electrons and atoms equal to the atomic number, and each electron that enters in orbitals increasing energy. So you would not have like this. You would never have, here's hydrogen, and go 7s1. No, it's going to load the first quantum level first, right? It could be 7s1 if you shocked it with electricity. So what happens, like if you think about it, here's the atomic orbitals. Let's put this like this. I'm just putting this out here. Let's go out to this for fun. And let's say this is hydrogen. And if you hit this with electricity or hit it with some kind of energy, you can bounce them up. And that was in the previous section. And when they fall back down, they emit light or something in some electromagnetic wave as a Planck's constant. And it could go up to 7. It doesn't want to be there. That's not the ground state. The ground state is what's normally found in nature. Normally in nature, it's not this. It's just 1s. This is what it would be, right? So that's how you kind of look at this. So you fill from the bottom numbers up to the top numbers, right? And so this is the way it loads. And this may be confusing for people to look at. The easiest way is just to read across the periodic table, and it makes it a little easier. There's a couple catches, right? So it's going to load 1s, 2s, 3s, right? But look at this. It's going to load 2p before 3s. Then it's going to load 3p, 4s, 3d. So I always found this diagram really confusing whenever I took chemistry. I just think it's easier to just look at the periodic table because it gives you how to do it. So periodic table is shaped a certain way. This is it unfolded. Now if you were to read across, you go 1, this is 1s2, 2s1, 2s2, 2p1, 2, 3, 4, 5, 6, 3s1, 3s2, 3p1, 2, 3, 4, 5, 6, 4s1, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 4p, so you get the idea. It'd be nice if it was like this, but they don't do it like this. In fact, they stick it all together in one, like this. But just keep in mind, you load across as you read. So it goes 3s, and then it goes 3p, then it goes 4s, 3d, then 4p. And honestly, there's actually a couple weird glitchy things here. 1, 2, 3, 4, Like this one right here, 1, 2, 3, 4, you're going to see weirdness here and here, right? And we'll get into the story, but 3D4 and 4D4, as well as 3D9 and 4D9, is uncomfortable for the atom. I say uncomfortable for lack of better words. Um, so it actually is going to steal the electron from this quantum number and put it here. So essentially, you're not going to have 3D4 or 4D4. Instead, you'll make your thing, and we'll get into it, 3D5, 4D5, and 3D10, or 4D10. And the one before it, in this case, it'd be 4S, they would make it a 1, not a 2. And you'll see, I'll repeat this coming up when we do more stuff. So they actually steal one from this one to place here to maximize the upward spin. All right. Let's take a look here. So this is a typical electron box loading diagram thing set up. And I have it so you read across, these are the D's, now you have F's, all the way down to the 6's, all right? So if I grab an element anywhere on my periodic table, and I'll show you how you do this, it's not too hard. Let's go to clear this. And let's grab someone like sulfur. Okay, everybody see where sulfur is? He's right here, okay? So I have 1s1, 1s2, 2s1, 2s2, 2p1 through 6, 3s1, 3s2, 3p1, 2, 3, 4. So when I go to my things to load them, right, and I'm going to make this the smallest thing possible. So this is 4s1, that's hydrogen. This is down, that would be helium, right? Then we have, that's the end of that row, right? Boom, boom. And we have lithium, then we have beryllium, okay? So we go 1 up for lithium, down for beryllium. You have 3p1 through 6. So look how this looks on our thing, right? Boron, carbon, nitrogen, oxygen, fluorine, right? So we can do this at boron, carbon, nitrogen. So we're going to go boron. This is what carbon would look like. This would be nitrogen, right? Then we have oxygen. Then we have fluorine. And our last one down would be neon, okay? That's what it would look like. So you can just imagine there on back is what it's supposed to look like, okay? So we go into the next quantum number, which will now be 3, right? Look, we have sodium and magnesium. So they would be on 3s. We go up 1. This is down 1. So this is sodium, and this is magnesium. Well, let's do our 3p's. And look how many p's we got. 1, 2, 3, 4, right? So trying this out, it'd be 1, 2, 3, and the last one's this way. And that right there would be our sulfur, right? So that's how you would do electron box loading on sulfur. The only ones that are going to be wacky is something like chromium or copper. Like I said, these guys are the ones that are going to act strange. Copper, silver, and chromium, molybdenum, they're going to not do what you think they're going to do. They're going to do something quite a bit different.